right. Hi, everyone. So today we have a talk by Hyunseung Kang from University of Wisconsin-Madison. So our rival UW organization.
The better UW, no?
Difficult for us.
Yeah, I know. That's I'm a man of one here.
All right, so a little bit of an introduction. So Hyunseung is an assistant professor at the Department of Statistics at the University of Wisconsin-Madison. His research actually soon to be an associate, so congratulations. His research is focused on studying causal relationships by using instrumental variables, econometrics, semi and non-parametric methods, network analysis, and machine learning. He's interested in applications to genetics, epidemiology, infectious diseases, health policy, education, and applied microeconomics. Very detailed list.
Yeah.
So today we'll hear Hyunseung speak about experimenting on students. Very controversial topic. Yeah, so hopefully you all enjoyed the talk. If you have questions and you're in the room, please just raise your hand and we'll call you. If you have questions and you're on Zoom, please just type them in the chat or also raise your hand to Zoom and I will let Hyunseung know that there's a question. If you could repeat the question if someone in the room says it so the people on Zoom can hear them.
Sounds great.
Okay, great. Thank you so much.
Yeah. Well, thank you for the wonderful introduction, and thanks Emma for also organizing this, and also Christine as well for organizing the visit. This is the most detailed information visit and also the most organized visit that I've been in the recent past for sure. So today I'll be talking to you about something that I've done during COVID, which is how to do experiments under privacy constraints. So we had a question during COVID about how to evaluate courses and how to do this in a way that would protect student privacy at the same time. So this talk will be about essentially how to run an RCT under privacy constraints at the end. So this is joint work with my former student, Manjusha Kancharla, who's now Dr. Kancharla, and she's now working, making a lot of money at an insurance company. And I'm definitely not in that. Anyway, let me just give you the overview of the talk. So essentially the outline is as follows. So we have a randomized experiment and beta privacy. And the idea is to essentially combine these two concepts to construct an RCT that actually allows you to have privacy guarantees, specifically differential privacy guarantees, a modern notion of privacy. And so to do this, to introduce this new design that we're going to introduce, we have to review a couple concepts that some of you might be familiar with and some of you might not be familiar with, or maybe all of you might be familiar with all the concepts. The first concept is a review of local differential privacy that was popularized in computer science and now merged into also stats as well. The second concept is on cheating. Specifically, experimental psychologists back in the 70s and 80s and even to this day have a lot of these very clever experimental designs. We're going to borrow one of these to actually and modernize it to answer the question of interest in this case, which is how to run a randomized experiment under privacy constraints. So we're going to combine these two distinct ideas to achieve our goal of RCT under privacy. And the modern twist really is not so modern in the sense that we're just using sample splitting, but just this has been repeated in crossfitting so many times. But essentially, this one additional piece allows us to get some nice guarantees at the end of the day. Now, there's some nice theory here too. It's not perfect theory, but a consistency about our estimator, asymptotic normality, some relative efficiency and privacy trade-off. Because the thing is, if you're doing an experiment under privacy constraint versus an experiment without those privacy constraints, we're going to have some loss in efficiency, but at the same time, we're going to gain in privacy. So there's a trade-off here that we're going to describe briefly in the talk as well. And the best part of this talk that I think, in my opinion, is actually we implemented this design and we ran this trial and we ourselves, myself and my student actually ran this trial in person and we collected our own data set to demonstrate this design itself. Specifically, we used this design to compare different modes of online lectures during COVID-19. What type of online lectures were most useful in the student engagement, student learning. Here the outcome is actually private in the sense that it should be private in the sense that these are student scores or student performance in the class in which are FERPA protected. And we want to still answer scientific questions of interest. And this is just an archive. A lot of economists like to do this where they have a paper along while they follow the paper. So this is one thing that you can definitely do at the end of the day. Okay. So with that said, let me just go through review. So randomized controlled trials is the gold standard to unbiasedly estimate the average causal effect of a treatment A on an outcome of interest. And essentially, how RCT works, probably almost all of you are familiar with this, is you randomly assign certain participants to treatment AI equals to 1 or control AI equals to 0. And then at some point, you observe the outcomes between the two arms. And then taking the difference between the average outcome under the treatment arm versus the average outcome under control arm gives you an unbiased estimate of what's known as the average treatment effect or the average causal effect. Now, this is used a lot. It goes back to many decades, but it's also used religiously in health and some education, tech for sure, and A/B testing every time some products release. Social scientists also have used this a lot in the recent decades to actually understand causality. Now, one of the implicit assumptions in the RCT is the fact that the participants must be willing to share their true response to the outcome that we're interested in measuring. But what if this response that we're trying to measure is actually private or sensitive in nature? So let me just give you some examples of those type of outcomes just to give you and so before that, what if also the PIs want to share experimental data containing sensitive responses too? So a lot of times when you look at RCT data, specific clinical trials data, you rarely get to look at the individual level data. You get a summary statistic of it, and to get the individual data actually requires a lot of effort. And in fact, there's a trade-off here in terms of how do we do transparent science where we can replicate every step of their analysis and or even combine the RCT data, previous RCT data with new RCT data to get it boost power while trying to preserve privacy at the end of the day. And what if the PI wants to actually release this individual level data that they run an RCT trial without compromising the participants' privacy? And so that's another aspect of thinking about why this is necessary. And also some responses are simply protected by law. And so these are examples of the FERPA, which is, I think, even predates HIPAA, which some of the biostat folks might be familiar with. This protects pretty much most student records. You need to get individual permission per record and per characteristic to actually get anything related to and get anything out at the end of the day. And HIPAA is the one that any biostatistician will be familiar with. Also, there's GDPR, which is the European version of this privacy law trying to protect data privacy on online data privacy. And California have its own version, I think. And there's essentially one example of this that comes up a lot. And the one to your right, I guess, or yeah, right on the screen is this voting experiment that Facebook did to examine whether having your friends participate in voting would affect participation rates and all these other things at the end. Ideally, voting pattern behavior should be private if possible, while still being able to understand the effect of this peer influence at the end of the day. And so what they did was actually collected voting records data from most states that they did to essentially assess whether having this was useful or not. And on the left-hand side is what we did when we actually randomized when we did this trial, where we had a question in our classroom where all the lectures on Zoom. And the question was whether the instructor's face should be on Zoom while lecturing versus not on lecture. And the reason for this, why the question is important, is because there's bandwidth issues in certain rural parts of Wisconsin to get video feed data. And so having a pure audio lecture is actually, from a bandwidth perspective, much easier to deliver than having a video feed. Now, what an interesting scientific question is, does that harm students' outcomes at the end? Because having an instructor there and presenting whatever lecture material might actually make the student more engaged than just a pure audiobook recording of lecture slides at the end of the day. So there was a sensitive outcome. There was an outcome of this question was of interest to our department. And this is essentially, and the outcome here is various outcomes we measure, one of them being student engagement scoring of whether they score correctly on a question or not. And really, in these cases, these responses should be privatized. And how do we, really the fundamental question is, can we still maintain their privacy while learning something scientifically useful through the RCT? And that's what we're trying to do. How do we estimate causal effects in an experiment while protecting individuals' data privacy, specifically their response to treatment? So this, oh yes, go ahead. Yeah, so in this particular experiment, we actually just asked them point blank, did you pay attention in lecture? So because I didn't notice before going in, there are some standard questions to ask about student engagement in the education world and the evaluation world. So we asked the exact same questions that they did. So we can compare our results to their results, and their results are even, we can't access their results. Whereas our results, you can actually see, and I can actually see the individual level data. Okay. I think I repeated the question. I apologize. The question was, how do you measure engagement? And the answer is, yeah, there's a standard set of questions that in educational that measures engagement by just asking them point blank how this. Yes. we asked them during the lecture. So at the end of this lecture that we did, there was a 15-minute module on randomized controlled trials, actually. That's and that was sent out to undergraduate students in the classroom. And at the end of that lecture, we asked at the end, did you participate in the lecture? So yeah. So this is just a diagram to explain the state of privacy and randomized control experiments in a way that's trying to explain where we are in the scientific world. So on the y-axis is maximizing data privacy. Again, this is not in any sort of meaningful scale, but at the upper end is you maximize data privacy, and the lower end is you didn't maximize data privacy. On the x-end is maximizing scientific value. So if you go farther to the right, it means you're getting more science out of it, getting more estimands out of it, getting more identification out of it. If you go closer to the origin, you're getting less out of it at the end. Now, if you want to maximize data privacy while minimizing scientific value, it's the one simple solution, simply not run an RCT. Just don't do it and just guess what the people will behave. Now, this is not what's done in practice. And in fact, nobody does this. So somewhere in between is you lock up the data. So this is clinical trials data and only share summary stats at the end of the day. So the idea is that you share the protocol which was run, but not the actual individual data that was collected at the end to actually run this thing. Now, somewhere in between, this is in the database world, is to share aggregator anonymized data sets, or L-diversity, K-anonymity, are essentially different ways of aggregating individual level information to an aggregate summary so that some notion of privacy is preserved. And here it's kind of not perfectly maximizing Davis privacy at the extent of like locking up data, but at the same time, it is getting a little bit more granular information about the data, something that we want to learn about the population. And finally, at the end of this, at the extreme end of this, to run every RCT you want, and then share every data, individual participant data as much as you want. Now, that's also not what's currently done in practice. And most of it happens somewhere in the middle here. And that's what the current state of the world is. Now, the problem in this middle world is that there are a couple problems. One is that some of these existing methods of aggregating and anonymizing information isn't actually private. And so there's wonderful papers in the differential privacy world that shows that some of these aggregation methods actually don't work. And one of them, I think Sweeney, one of the authors, just said something about 87% of the US population can be anonymized just from merging a couple anonymized data sets at the end of the day. And so that's quite a bit of anonymous. So anonymization alone isn't sufficient to guarantee whether your individual data is protected. And this is a classic example is also this Netflix data, where I think they were able to re-identify users using the IMDb data, even though both of them are anonymized at the end of the day. Now, the other problem is that they're the exact trade-off between the privacy and the maximizing scientific value, specifically in our case, estimating causal effects is not clear here. It's specifically, what's the trade-off between getting root and inference versus a loss of privacy that we get? So those are the two current problems in this current state of data privacy in RCT world. So our approach, again, in a diagrammatic sense, is doing something here where we're not trying to maximize all possible privacy in the sense that we don't ever run an RCT, nor are we trying to maximize scientific value at the same level as running an RCT and being transparent about every single outcome at the end. But we're trying to still run an RCT while making some guarantees, specifically differential privacy guarantees about our outcome so that the outcome cannot be recovered up to differential privacy guarantee. And that's what our approach, RPRCT. So that's the review of RCT and a little bit about data aggregation. Let me just give you a review of a very, very brief review of differential privacy. So this concept was introduced, more formalized by Cynthia Dwork in 2006 and even papers before that. And the idea is very simple. This is just one explanation of it. So let's say you have a participant's response, some true response at Y, and you have some algorithm that takes in this response. And what this algorithm does is it spits out a privatized version of this response at the end. And then this algorithm is the characteristic of the algorithm is known as differential private. So if an algorithm does a lot more privatization, it's more differentially private. If it does less privatization, it's less differentially private at the end of the day. So just to give you an example, if my, this function that takes in the true response data, spits out 1 for every value of Y, this is what's known as perfectly private or zero differential privacy. Because with 1 alone, this is what we get to see, privatized response. There's no way to recover the true response because every value is the same at the end of the day. And this is in the DP world known as zero DP. Okay? There's no privacy loss. The other end is where you essentially this function, the algorithm always spits out the original outcome. So this is an identity function. In this case, you can always recover what the true person's value is. In that case, and there's no privacy, or in the DP world, it's known as infinite private, deep differential privacy. Okay. And somewhere in between is known as epsilon privacy, epsilon differential private. Okay, and so anywhere between, as epsilon increases, you lose more privacy, and epsilon gets closer to 0, you get more private at the end of the day. So that's differential privacy in a nutshell. And just to give you a sense, this is not something abstract or mathematical. People use this concept in your favorite mobile devices. So Apple uses this to protect health data. So if you ever wear an Apple Watch, it says it's stored in locally, that there's a differential private mechanism being done to store that thing privately as well. And the epsilon they said is 2, according to their old white paper at the end. I'm not entirely sure how they said it, but that's what they do. Safari and emoji. So this is when you type, and there's a predictive text algorithm that's done it. There's a back and forth between the server, and obviously you don't want text that you're typing to always go up to the server unprivately. So there's also differential privacy mechanism operating, and there the epsilon is according to this white paper set at 4. And then there's a QuickType also set at 8 as well. Uber also uses this. Google Chrome also uses this whenever you type in an address to see if the address is matching to some kind of a database of like addresses that it's going. So this is not so this concept is widely used to measure privacy and to guarantee some level of privacy. And formally, just to give you a sense of this formal definition of privacy. So essentially, for every individual I consider a response Y to be a sensitive from some sensitive response to some sensitive question, and we say a randomized map epsilon is epsilon 0 differentially private. If for all possible values outcomes, essentially you can't differentiate, you can't distinguish them up to epsilon, it's an exponential of the epsilon. So if you've seen this, you're probably very familiar with it, but this is essentially just the notion that I talked about, just a bit more formalized. Yeah, okay. And essentially what this definition and words tell you is that if there are 2 different true responses, Y and Y prime, it's very difficult to tell apart the difference between these 2 true responses after privatization up to epsilon term. So you have, let's say, the 2 values of the true response being the test score being 100 and 92. After privatization, it'll be very difficult to tell them apart. And the difficulty to telling them apart is measured by this epsilon. But then if this is confusing the other epsilon definition, so the slide is essentially this conceptually identical in terms of what this is doing. Okay. So there's a very famous differential private mechanism that's been known since the 60s, and this is from the experimental psychology literature, and this is known as a forced randomized response. In fact, when differential privacy was introduced, this was one of their first examples of talking about it. So how does this thing work? Is let's say our final question at the end of after running this trial is, did you actually pay attention to lecture today? And we just point out blank ask. Now, Bob, one of the participants, wants to say he didn't participate. He was just playing Minecraft on his for the first 2 minutes at the end of the day. But what the FR algorithm does is to protect Bob's response. It was essentially say, okay, if the spinner, which is random, lands in red, then you always say no, irrespective of what Bob's true response is. If the spinner lands in green, the Bob will always say yes, irrespective of what his true response would be. And if the spinner lands in blue, Bob will answer honestly. So in this particular example, the spinner, which spins randomly, lands in red, and then Bob will always say no. Okay. And the key here is that I don't get to see, as an investigator, where the spinner landed, nor Bob's true response. Ultimately, I only get to see this very final point. And from here, I don't know whether this no is true no, or whether this is a forced no in the literature, or is this a forced yes at the end. So there's a privacy mechanism operating here, because this privatized response does not tell me whether his true response was a no or yes. And this is done by this forced response, randomized response algorithm. And so the spinner can land here too, just to give you an illustration. And then the Bob will always say yes. And even since I only get to see this and not the spinner, nor what Bob's true response is, I can't tell whether this yes is Bob's true response to yes, or whether this is yes because the spinner said it. I should tell yes. Okay. And so there's essentially this there's data privacy through plausible deniability is what people call it. When I get this, there's a plausible Bob. There's no way I can tell whether it was a true yes, true no, or a partial yeah in one of those 2 cases. Okay. So just to give you a sense of how all this relates to the epsilon term I mentioned, this exact shading of the area shading corresponds to an epsilon of 1.1. And the reason for this is essentially, and you can kind of tell, is that as epsilon gets smaller, the proportion of the area and Bob has to answer honestly gets smaller. And that kind of makes sense. Remember, epsilon getting smaller to 0 means perfect privacy, and epsilon getting larger means no privacy. And so the opportunity for him to answer honestly is getting smaller, would imply that epsilon must be getting smaller. And the opportunity for him to epsilon gets larger, that blue circle should get larger as well. And so that's roughly how this epsilon and the pie chart roughly corresponds at the end of the day. And that exact pie chart here is epsilon equals 1. This is exactly epsilon equals 5.1, and so on and so forth. So before I go on to this slide, so we thought we're done. We can apply differential privacy, whatever their response is, get them to do this, and then say, and we collect that y tilde and then run an RCT and we'll be done with it. But the problem is, and if you taught a class ever, students lie. Okay, and this is a particular type of lying that happens at the end. So let me just illustrate this with a particular principle that we saw when you were in a pilot study of this. So we asked this question, did you actually pay attention in lecture today? And Bob's true response may be no. And the spinner says that you should say no. But Bob, being Bob, might not follow the spinner's direction because he's Bob. You know, maybe he does. He just wants to lie every day, and he just wants to say, "I paid attention every day," even though the spinner told him not to say yes. Okay, so Bob might just say yes just to impress the professor. Bob might just say yes because it's a human nature maybe to lie, or because Bob can lie. And so what we would do is essentially, instead of following the protocol of the FRR, he would actually deviate from the protocol and cheat and say yes, just to impress. Yes?
Couldn't this part be done by an algorithm instead of by the student?
Yes, so that's a great. So the question is, can this algorithm, can this spinner be done by an algorithm, not by a student? And yes, and actually in an implementation, this spinner is done by an algorithm. But the thing is, the student gets to see the result of the algorithm before submitting their final answer to us. And then because that was the IRB part. We couldn't simply take the spinners, and then get it out. We had to still give the student the opportunity to change their response at the end. Yeah. Yes. Yeah, exactly. And so that's what we observed too, is that some students simply might feel just too uncomfortable saying no, especially even if the spinner landed no, and I can't tell whether it's a true no or not no. The student might not understand this principle, which is indeed what happened. And the IRB officer also took a hard time understanding this procedure as well. So it's very possible that the student could simply just ignore this instruction and say whatever they wanted at the end of the day. And the worst part of this, from a statistician's perspective, is I don't know if he did this or not. I don't know if he cheated or not. I don't know if he followed protocol or not. I don't know what happened in between this problem, because at the end of the day, I only get to see this thing. Okay, so this adds a real level of complexity. And as you'll see, we actually are able to estimate the number of people who do this in the population, in our study group, but it's fairly large. It's not like 1 out of 130 students. It's about 30 to 50% of the students who do this. So it's not a non-trivial proportion of people who do this. Okay, so so I just talked about cheater. So informally, what is a cheater? So a cheater is essentially people who deviate from the protocol. That's what the informal sense is. You're supposed to follow this protocol that we laid out, but then they decided not to for whatever reason, measured or unmeasured. Okay. And just as an example, you're supposed to say yes, I paid attention today you're saying yes, I paid attention lecture today, even though when they're supposed to say no by the FR's instruction. That'll be cheating because it's deviating from the protocol of the FR. Okay. The other one is, the other thing is the no here could be forced no or truthful no. And I don't have any idea telling whether this no came not only from his true responses no and following the protocol. There's an added layer of noise here, which is that they could lie and then just say no out of just spite. Okay. Now, formally, what this means is that an individual is a cheater if essentially the algorithm's output is different than what we got at the end, and the probability of this is not great. It's not exactly equal to 0. That's the formal definition of it. So that's essentially this algorithm privatizes something, and we're supposed to get exactly what the algorithm said, which is y tilde, but we're not. This is what we observe, and this is different from what the algorithm produces at the end of the day. And the challenge here is I don't know from an investigator perspective, only observing yi tilde, whether this yi tilde came from this being equal to each other or this not being equal to each other. I don't know whether a no, yes, I paid attention in lecture today is yes from an FR following protocol, or yes because I lied and I still wanted to impress the professor in the end of the day. And and without knowing that, essentially it becomes much harder to answer the original scientific question, which is what is the effect of turning on video camera or not on, let's say, whether you participated in lecture or not, you paid attention in lecture. Okay. And to my knowledge, again, I'm new to differential privacy. I don't think this literature has dealt with this case. Essentially, the way we see it is essentially the differential private algorithm was not faithfully executed. There's an implicit assumption of differential privacy, at least to my view, where whatever algorithm that you propose actually is faithfully executed. The Laplacian noise is faithfully added, and nobody messed up with the Laplacian noise, or nobody messed up with adding some type of noise. And that's very reasonable because most of these are done by an algorithm. But if there's a human element involved, especially in our case, where the human has an opportunity to cheat and deviate, then this becomes a problem. And so I think this is the difference between one of the literature, what's done, and what we do at the end of the day. And that's more complexity to the problem. So how do we deal with cheaters? Because this is a real problem, and this has happened, and we can actually show how many people are cheating. One way is to do nothing, because we can assume it away and assume that there are no cheaters and everyone's an honest angels at the end of the day. And that seems very, and you can definitely do this. Or maybe the other kind of a saving grace measure, hope there are a few cheaters. Maybe out of 100 participants, only 2 did it. Therefore, when you take the AT at the end, we're still fine, up to 2 estimate. But that wasn't satisfying to us because ultimately we know that this could contaminate results significantly. Okay. The other way is to actually figure out a way to find out whether you're a cheater or not cheater. Okay. But if you think about this question far and hard enough, the problem is essentially to do this, you have to ask more questions. And so there's a literature in experimental psychology about these validation questions. Survey analysis does too. You just ask a question in a survey that you know the answer to be the case. So the simplest example is, what is the answer 1 + 1? Okay, and then everybody knows that it should be 2, and if you lie to it, then you obviously, that could be an indication that you might be lying in the other question. That's that simple example, but there are more complicated examples in political surveys that people do because they already have a proportion of people who identify a certain way, and if it deviates a lot from this proportion, then there's these kind of validation questions that experimental psychology used in the past, and it's also survey design used a lot too. The problem here, though, is that cheaters don't have to behave uniformly across every single question. They can lie in one question, they can answer honestly in another question, and they can answer honestly in a different question and cheat in a different question. So having this validation question doesn't really give us a full sense of whether they're going to cheat in the question that we ask instead of the question the other question at the end. And we thought about this long and hard because we didn't know how to deal with this very complicated problem. We don't know who the cheaters are. In addition, do we add noise to it? And we thought about asking more questions, but ultimately this required essentially asking more things about the person than we might be comfortable, especially sensitive things about the person at the end of the day. So this boiled down to essentially being able to know to a very, very sensitive degree whether you're actually behaving honestly or not. So our solution actually came out of just reading Victor's work and just revisiting sample splitting over and over again is sample splitting. And essentially, the idea here is to use slightly 2 different spinners that you saw and actually use that as an extra moment condition to identify the proportion of cheaters. And we can actually get this very easily. And so it's a very simple solution. And let me just illustrate how this thing works in a design. So we have N participants that participate in the study, and we initially do a sample split on those N participants. So one of the subsamples will get this spinner as their spinning randomization mechanism. The other subsample of N participants will get this spinner, okay? And if no one cheats, there's a certain proportion of people who would say yes that we can expect. If no one cheats, and then the same here. If no one cheats, we can also calculate the expected proportion of people who would say yes. That is, if everyone follows the protocol, we can actually calculate this probability easily. And the idea is that under the assumption of no cheaters in both cases, we know the expected difference between the yeses between these 2 samples. And whenever this test statistic deviates, we actually can know there's a cheater at the end of the day. And part of it is because we have a slightly different proportion of people answering honestly that we're exploiting at the end. And essentially this concept has been described in Clark and Desharnais as another. And again, I'm delving into experimental psychology literature for the past couple of years now, especially during COVID. And they're really clever designs on how to really make sure you identify the specific mechanisms of a causal effect. And this Clark and Desharnais paper actually talks about having a slightly 2 different FR to detect people who cheat on an exam, a standardized testing. Now, in that paper, they actually have to assume that additional assumptions about the cheater's behavior, and we just generalized this to allow for arbitrary cheating behavior. Specifically, their paper assumes that every cheater will always answer yes to the question of whether did you pay attention to that lecture or not, irrespective of cheater characteristic. We allow the cheater to say yes or no, depending on how you want to phrase that question at the end. So that's the big innovation there. And the reason they probably weren't able to do this is because they probably didn't realize this GMM that comes from essentially having slightly two different randomized mechanisms that you have, and you can identify an extra parameter at the end. Okay, so we have every ingredient. Yes, question.
I guess, is there like an assumption when you say you know what you should expect the difference that in your sample split, the percentage of yes and no, like true yes and no, it's the same?
Yeah, so under the null of no cheaters, so if everyone follows the FRR protocol, then I know the expected number of yeses, because it's essentially the proportion of this green circle plus the proportion of yeses, honest yeses here. And the same thing for here, will be the proportion of this thing plus the proportion of people who say yes here. And the proportion of the proportion of people who say yes here because sample split. So under the null of no cheating, I can actually get this expectation. And then essentially it's a hypothesis test. Under null no cheating, I know what the expectation looks like. I can also calculate the observed yeses. And if it deviates, then it must be there's a cheater in effect, essentially, because all the assumptions of a randomization sample splitting are held. So this is our design. Since we now have the ingredients, it's pretty much, so you're known to be in review like you before, collect pretreatment covariates, and then you do this random sample splitting to detect cheaters. And so one of them will be randomized. This is what we call an FR algorithm 1, so just another differential, one type of differential private mechanism. The other one will be privatized with a different private mechanism. And then after this randomization, you would randomly assign people to treatment or control. And the same here, and then you get the following output, the privatized outcome. So this privatized outcome again could be cheater responses. They could just always say yes or whatever they wanted to, even if we're in this bucket. The treatment assignment, whether they got the treatment or control. S is whether they were in one of the sample splitting variables, and the other characteristics about the person that they wanted to report at the end.
Are you choosing the two mechanisms? Like, I mean, so sample splitting is arbitrary, and you make this seem also completely arbitrary, but would the results vary if I use that?
Yes. So the question is there a better way to ascend? Is there more of a finer art to choosing these sample splitting mechanisms? And the answer is yes. And so we characterize by relative efficiency. So depending on how big the difference between these two pie charts are, it essentially allows us to be more efficient or less efficient. But then it comes at a privacy loss. And so there's a trade-off that we'll talk about. But yeah, it's a great question, and that we'll talk about. Because conceptually, it's very intuitive. It's very similar. So if this pie chart looks very similar to this pie chart, then we have a harder time detecting proportionate cheaters. And what means that there's going to be consequences in terms of efficiency down the road. But if this is a lot different, then it's much easier to detect cheater. But then you get into this question of you get a privacy loss because this has to be larger. The blue circle has to be larger. So there's a trade-off that is implicitly being made here. And so just to be clear, compared to like an idealized RCT, there are two additional steps. One is the sample splitting part, where we would split the sample into two parts to run these two FRR algorithms. And the second, and again, this is to measure cheating behavior. And the second thing is the FRR algorithm, which is to enforce the privacy constraint if the people follow it. Again, students are not expected to follow it, and they don't have to follow it. That's perfectly okay. And so the first theorem about the design and the data we get is that this this privatized response is differentially private. Okay? And so this shouldn't come as a surprise, but the key here is that only we can guarantee the non-cheaters responses to be differentially private. We cannot guarantee cheaters responses to be differentially private. And this is a point made because if cheaters, for whatever reason, are acting kind of not intelligently and actually always giving deterministic responses, then by the theory of differential privacy, you can actually always recover back what their response would be. So just as a clear example of this, if for whatever reason the cheater's response to us is 1 minus the opposite of it all the time, but by differential privacy theory, I can always recover what their true response would be. Okay, and so this is just a limit. It might be considered to be a limitation differential privacy definition, but if you think about this hard enough, at some point, if an investigator realizes that he's always flipping answers from what it's supposed to be doing, then it's possible to detect. And that's why for cheaters, we don't have any differential privacy guarantee. But for non-cheaters who follow the protocol, then there's definitely differential privacy. And that just comes from the FR protocol. Okay. And so this theorem, to some degree, suggests that people who participate should not cheat to guarantee privacy. And in fact, there's less incentive to cheat. But then, despite this, people do it anyway. And we'll show how many people still do it. There's also nice properties of differential privacy about immune to adversarial post-processing. And this is a work by Cynthia and then Aaron, and about how differential private algorithms, even after multiple processing, is still retains the same epsilon privacy guarantee here. Okay. Yes.
So this seems kind of general, like the RCT part is, you could have had something without the RCT part, like a statement about differential privacy in the case of cheaters.
Yeah, so that will be, that's what one of the reviewers said. This is general enough, but apparently there's a paper I didn't know about differential privacy that has dealt with this case, but it's my part for not being able to go dig in deeper, but there is apparently work done on people strategizing to cheat away from the differential privacy mechanism that was discussed in the early 2000s. But yeah, I think this is another way of looking at the problem. If you just wanted to get rid of the RCT part entirely.
Is there something inherently non-private about RCT that doesn't exist in other aggregation methods, like where you complete some sort of application of the population?
Yeah, so I mean, are there anything inherent about RCTs that are not private? Yeah, I mean, ultimately, at the end of the day, an investigator has to collect outcome data, individual outcome data. So in the context of here is a student test score, student performance data in general. In the context of like certain evaluations of psychiatric treatment plan, it's very sensitive questions about your mental health. And those things are, even though the investigators are collected at the end of the day to evaluate different kinds of treatment plans for certain kinds of psychiatric disorders, ultimately the participant needs to be honest about their feelings of it at the end of the day, and they would ideally like to not even share this. But then from an investigator perspective, they still want to know whether certain types of treatment are more effective at the end of the day. So I think even in those RCT cases. Yeah, exactly. Getting the individual level, and it's really, and some RCTs it's just not a problem. Like if you're doing an RCT on cells, and unless cells have privacy rights, it's probably not going to be like, let's say like you do like there's these CRISPR experiments now, and some people are doing these kind of not RCT design, but these kind of similar RCT design. I don't think this is going to be a useful mechanism. But for other social science, political science, especially voter behavior, or even mental health, I think there are a lot of applications. That's our opinion. So let me move on to, so the first theorem was about the response being differentially private, so that there is a privacy guarantee that comes from an RPRCT. The second one is about identification, the causal effect itself. So let me talk about just the assumptions of identification under the regular RCT. So typically in a regular RCT, you assume these three things. Actually, it depends on which world you came. If you came from the Rubin world, it's called SUFA. If you came from the Robbins world, it's called consistency. And I think there are different flavors of it. Pearl, I don't think believes in this. I think this is the axiom. But in any case, so there's a SUDVA, and there's randomization of the treatment, and then positivity and overlap. And those are typically satisfied by design of an idealized experiment. And in those cases, then you can actually identify this causal effect, which is the contrast between potential outcomes and the treatment minus under control, as simply the difference in means between these two parameters at the end of the day. Okay, so that's what an RCT does, and the RCT by design guarantees these three assumptions. Okay. Now, our RPRCT also guarantees those first three assumptions by design. The fact that the treatment was randomized, the fact that the SUDVA holds, and the fact that the probability of receiving treatment control is positive at the end of the day. Okay. The other thing that the RPRCT guarantees is that the sample splitting was done randomly. And if you write that formally, it's essentially that the sample splitting variable is independent of all these other variables that's currently collected in the data. The other one is that the spinner is random, which is designed by algorithm. We implement an algorithm to run this spinner, and the spinner is not doing something crazy behind the back. It's truly random, and so that's also formally written as PI is independent of all the variables that are measured at the end. This one is just an extension of the treatment randomization, just to make the theory a bit more cleaner at the end. So this is also implied by the fact that if you combine all this, the treatment is also independent of all these other variables that we collect in the data, that's observed and not observed in the data. And again, just to be clear, AI is treatment, SI is a subsample indicator, PI is the result from the FRR spinner, and the CI is a cheater status. Now, there are two additional assumptions that we have to make to get to the causal thing, which is the effect of the treatment. One is, I think, plausible. The other one is what people in the causal inference call the heroic assumption. So let me first talk about the A8, which is that there should be at least some honest people in the group. Okay, this is just faith in humanity. And I believe there is at least a couple honest people. And so you just have to believe that whoever is participating in the trial, some of them are honest at the end, okay? And so and I think that's a plausible assumption unless everyone's evil. The second one's a little bit, the A7 is a bit more tricky. It's just essentially saying that the cheater's response to the privatized response of the investigators, independent of the treatment assignment, given the sample spinning variable, the spinner indicator, and their cheater status at the end of the day. And this one essentially says is that in words, what this says is that the cheater, if you're a cheater, you're not changing your behavior, specifically your outcome behavior, whether you're in the treatment arm or in the control arm. So going back to the lecture example where the one had the video and one had the audio lecture, the cheater, as a cheater, you're not responding differently as a cheater had you watched the video versus had you not watched the video in this sense. Now, this is a innocuous assumption, especially if the treatment is blinded. If the participant does not know what type of treatment they're getting, so in a placebo randomized controlled trial, there's no way they could act upon the treatment information to actually make a decision. Yeah, so that's a great point as well. So it's a heroic assumption we have to make, is that essentially we have to assume that if they saw the professor, they're acting differently than had they heard the professor, because the voice is the same. Yeah. It's just that one is just masked at the end of the day. And this is something that we have to admit that it is part of the thing that we need in order to understand. The reason for this is somewhat necessary is because if the cheater has also the opportunity to cheat based on whether they were assigned treatment or whether they're assigned control, then there's no way to tell apart whether the treatment effect is coming from the treatment or from the cheating behavior entirely. That's essentially the reason why this is. Yes? So what's the difference between the cheater and the yes, so actually there's a connection there. The 2 slides from now, there's a connection between non-compliance and IB as well. Actually, the identification strategy relies on an instrumental variable, which I'm intimately familiar from grad school. And so to that end, so consider an RPRCT and suppose these assumptions hold. Again, I think except for the cheater response behavior, I think, again, as long as you have a reasonably positive faith in humanity, I think rest of it plausible. You can identify the treatment effect, which is defined as the contrast between the potential outcome under treatment under control among honest participants by this formula here. It's essentially the difference in means in the treatment arm and the control arm divided by divided by these parameters. R and R prime are essentially the areas of the pie chart, that the blue area of the pie chart we know a priori, and this lambda is the proportion of cheaters. And this lambda proportion of cheaters is also identified by this formula as well, which is essentially the mean of this thing under the one sample arm plus some weighted mean of the outcome under one sample and the weighted mean of the outcome under another sample at the end of the day. Okay? So you can identify how many proportion of people cheated, and you can also identify the treatment effect among honest participants, non-cheaters. Now, let me just illustrate this theorem a bit more in words. So let's say we have complete faith in humanity. Everyone is honest, no one's lying on anything, and everyone is honest when they're participating in it. Then what this theorem says is that the RPRCT identifies the ATE that you would identify from, and not only that, it guarantees differential privacy. Whatever outcome that I get, the privatized outcome is differentially private, as well as I can identify the population ATE. And this, and in contrast, RCI, just a regular old RCT identifies the AT alone, but that doesn't guarantee differential privacy. So our design allows additional guarantee of differential privacy at the expense of, again, adding noise. And we're going to, again, talk about suffering variance consequences down the road. Now, let's consider the opposite case. We have no faith in humanity, and everyone's a cheater, okay? And so every participant just cheats. And what happens there is that then if you think about this a little bit, there's no way to actually, for RPRCT or even an RCT, to get any effect estimate. If everyone's cheating, there's really just no way to estimate anything about the treatment's effect on the outcome at the end of the day. Okay? Yes? Exactly. Yeah. So if all of our honest participants, essentially, we're identifying the same thing as the RCT AT, but we just add more noise to it. So that, and that's why we pay a penalty, because we add that noise to guarantee differential privacy, but we're still identifying, at least in the limit, the same thing as an RCT would. Now, ideally, I think in real life, and my view on the world is that there are probably some honest people and some are not honest people. And in this case, what our theorem tells us that we identify the treatment effect among honest participants and guarantee that those honest participants have their differential privacy guarantees in terms of outcome. And this is actually very similar to the local average treatment by Angus, Imbens, and Rubens. Specifically, in that literature, if you're not familiar, it's identifying an ATE among a complier population, which we don't know who it is. The complier population is nebulous subpopulation that exists, but we don't exactly know from data whether you're a complier, a non-complier, defier, always taker, and never taker. And in fact, the identification strategy, you saw the difference in the outcome at the top in the numerator, borrows from this identification strategy for the late at the end of the day. And yeah, and the same thing here in both the RCT of non-compliance and the RPRCT, we cannot observe who's a non-cheater from the data. But that's not, but we can identify the treatment effect among the non-cheaters at the end. Now, I think I have about 10 minutes. So this is just estimation. So now we have identified this thing with data. How do we actually plug in values and estimate the treatment effect? It's very simple. This is just a difference in means estimator, multiply by some constant here. R and R prime again are just a different representation, the pie chart area, the blue area specifically, and the lambda is the estimation of proportionate cheaters at the end, which is just, again, all these plug valued in, is the sample mean of different one arm versus another sample splitting arm. And then this is just straight up from Jun Xiao's book, or whatever your favorite textbook that you guys use here to prove math stat. It was Bickle and Doxson for me. For other people, it's something else. This is just straightforward to show that it's asymptotically normal, so you can get a p-value at the end. Now, one thing that that you might have recognized is that we are adding noise to the problem to guarantee differential privacy. And essentially, that means we're diluting the signal. And how much dilution happens is an important question, because if we dilute it too much, we lose power. And we need more samples to actually get it. And that defeats the purpose of actually running as RCT with the smallest number to guarantee, make sure that not as many people are exposed to the experiment to potentially reveal their privacy. So there is we characterize the relative efficiency between the estimator, the tau diff, which is just the regular old estimator from RCT versus and from the data you got from the RCT versus the variance of the estimator that we just saw before, where that data came from RPRCT. Now because both of them are technically identifying two different things. One is an AT among non-cheaters, and the other one is just a regular old ATE. We had to assume, just pretend for a moment, in the ideal world where there are no cheaters, how much are we losing in terms of efficiency? Because if we don't do that, then the RPRCT is identifying an AT among honest participants, or the RCTs are identifying hopefully an ATE among everyone, but if they cheat, then maybe they don't actually identify anything. So this is just that lambda is 0 for that reason. And this is a fairly complicated formula my graduate student worked on to figure this out. But essentially, the long story short is when the privacy loss is infinite, this relative efficiency difference becomes 1. So if you're willing to tolerate infinite privacy loss, essentially our RPRCT essentially in the limit converges to the regular RCT if the privacy loss is going to infinity. And this allows you also to choose an epsilon term, because this epsilon term depends on this epsilon through these terms here. And here you can kind of see what your tolerance for relative efficiency loss would be. And here our recommendation, at least in the paper currently, is to get based on this formula on how much you're willing to tolerate loss in terms of efficiency gain. You can kind of compute the epsilon necessary, and then maybe use that also to back out a power calculator at the end. And also this depends on tau 1 and tau 0, the true population's effect estimate under the treatment arm and the control arm. And this may have to be informed by subject matter experts. Similar to power, essentially you need to know what the treatment effect difference is a priori so that you can compute the number of samples required. And what we actually hope is that at some point, some data privacy standard comes in to actually set some more clear guidelines rather than some tech companies setting arbitrary epsilons for 2 for health, 4 for something, and 8 for something else. I think that's probably what's probably necessary. And there's a lot of work to be done to statistically characterize that trade-off. So there's also covariate adjusted estimator, because one of the, as I mentioned, we're adding noise to the system to guarantee differential privacy, which means that we're diluting signal, but we need to gain that back somehow. And then the one way to gain that back is by essentially collecting covariate information and then using covariate adjustment, similar to what you do in ANCOVA. And so there is a one way to do this. There are many ways to do covariate adjustment in RCTs or in trials. We just used the one that I was most familiar with, which is just the augmented inverse probability weighted estimator, which just, if you kind of know this form, it's essentially this form, where this function is just any arbitrary model between the privatized outcome among the treatment arm, and this is any arbitrary model for the outcome given under the control arm. And again, this nice thing about this is that you can specify this model function however you want. By double robustness property, they'll still remain consistent and asymptotically normal, so you don't have any penalty loss if this is completely misspecified. Yes.
So when you have covariates, there's no extra assumptions needed to guarantee the privacy for y hat or y, even if you do not do any post-processing max.
Yeah, so we leave X to be arbitrary as you want. So the student who's participating, and as I'll go through the next slide, can actually just leave the X part unanswered. So we have a set of X's that we ask. So what is your gender? Like what is your background? And like, did you like math before, kind of things? And those are, and we wanted to answer them. We wanted to force them to answer them so that we can get more information out of it. But the IRB said no, they still need to have the opportunity to not answer so that you can release this data to the public at the end, which is what we did. We release individual level, public level data. So that's, and so, but the thing is, for this theory, X could be completely missing. And then that would mean that this is a terrible model, and this will be a terrible model, but this estimator will still be consistent. For example, I could replace this as just a constant number 1, and I could replace this with constant number 2, or whatever the number is. And by the double robustness property, it will still converge to the treatment effect at the end of the day.
Well, my question was regarding the guarantee for privacy. If I have truthfully answered X, can I somehow like recover or go around the guarantee that you provided for the Y?
I see. So if the X contains some information about the cheating behavior, about the truthfulness of a response at the end. Yeah, so just to repeat the question, forgetting to do this. Yeah, so the question was, can I use some of the X's and the truthfulness of the X's to recover something about their cheating behavior? And the answer is you could probably. We haven't explored this. In fact, one of the future work is to use the X to better estimate the proportion of cheaters. If you notice the proportion of cheaters identification, it doesn't rely on X at all. And part of it is just because, that was sufficient enough to identify. But obviously, you can incorporate the X's to get a bit more efficient estimates of lambda. Yeah, that's a good question. So in the span of 5 minutes, let me talk about actually running this thing. And because it's rare for, even though we teach it that, statisticians always work with data. We always work with data, but we never make our own data. Somebody else makes the data for us, and we do the creative analysis and then scientifically useful analysis. So this was a rare opportunity where we got to create our own real data based on our own design, and then actually explore its consequences. So we're going to study the effect of different types of online statistics lectures on student learning. This has been studied, I don't know, but it has been studied in the past by various authors. Specifically in these online courses, MOOC courses in the past that predates COVID. And there obviously this doesn't come as a surprise, but students pay more attention to instructor present videos than if the instructor was not present. Thank you. And unfortunately, though, when you reached out to one of these authors for their data, they said this is private. So we would just have to rely on their information that the p-value is like, I think there's one of the papers, a 10 to the negative 11th with sample size of about 150, which was incredibly significant given, but we couldn't get the data. And so that's the problem of scientific replication here, is that we have to rely that data on, and I'm sure they did it honestly, but it's just that it would be nice to have that data for replication, but also to combine it with our data set to boost power. That was the other motivation for it as well. And so we are going to test the exact same hypothesis that they asked using an RP-RCT instead of their AB to RCT design. And so we did this in about exactly a year ago. About a little bit more than a year ago now. Am I getting that correctly? Yeah, a little bit more than a year ago. We recruited undergraduate students to listen to lectures on RCTs. We thought about which lecture topics, and RCT seemed relevant because it came full in circle. And also, this is a topic that was actually covered in 301. I know there are a couple of students at UW-Madison sitting here who are my undergraduate students in the past. So we had 70 students who volunteered during COVID. We set epsilon for now to be the same standard that Apple Health uses. So if you think Apple Health department is making the same privacy trade-off with epsilon 2, then we have the same guarantee as Apple Health in terms of differential privacy. So we think that's pretty safe. And our IRB officer was convinced too. That was the most important part. Then we can publicly share this sensitive individual level data because we don't even know what the true outcome is, but we can still estimate the AT, and you can replicate it as much as you want, do analysis, diagnostic plots, or whatever you want, because there's a differential privacy guarantee. And yeah, just to mention that we mentioned this because it took a long time to get this approval, to convince the IRB officer of a spinner on a slide on a Zoom call. This is truly random. Like, can you not see? Like, I don't know what the true test score is if I spin this thing. And that's actually something that we have to work as a statistician to really communicate this material in a manner that's easy to understand for not only regulatory body agencies but also scientists in general who may not be statistically inclined. But it took a while, but we convinced the person finally, and we thanked her afterwards. So the arm is as follows. So we have a one arm where there is no video, but the audio is the same audio, and the one other arm where there is my student Manjusha presenting on our RCTs. This arm about 37 people, this arm about 35 people. They're all randomized and split. There's a standard to do this covariate balance. Just trust me that covariate balance worked, and the paper has the tables exactly details. The randomization was good. And this is the FR instruction. So the instruction on the screen after watching the lecture is you roll the die, and the result of the dies are either 1, 2, 3, 4, 5, 6. And then based on 1, you have an instruction to answer yes, no, and all the other things. And then you get to click this die. And then they get to see the result of the die, and then they get to respond about the question at hand, whether they pension that lecture honestly. So this was the spinner that they were presented with. Okay. And now they don't have to follow this. We don't know if they follow this. We don't know where this landed. We never get to collect this information at the end. Okay. And the thing this roll the die is actually rigged, much like the pie chart having different blue areas. There's a probability, it's not 1/6 all the way through. It's a little bit different based on the sensors. And the participants are also known about this probability as well going in. And even if they didn't know, they can ultimately cheat too. So they can ignore this entirely. Okay. So the response is, I found it hard to pay attention to the lecture. Do you agree with the statement? And yes. And this is one of those questions I didn't know was standard in evaluation world to ask, and there's a standard set of questions that you ask in evaluation. And the result is that as it's not so surprising that student follow very easy to pay attention to videos with instructors face on it, and the AT effect is about negative. So essentially, if you participated in the proportion of at least 32% more people as students found it to be more easier to pay attention when the instructor face was present versus when it was not present. And the most remarkable thing for us is the confidence interval. Even the sample size is 72 and we add random noise to it, we're still able to get a significant effect at the end. That could mean, and also cheating behavior. Cheating behavior. And then the first surprising thing is they're 24% cheating. So out of the 75 people, about 25% of them are cheating. Okay, and so this is a large proportion. You thought 2 people? No, it's actually higher than we anticipated. And this also results agree with all the RPC. But the key here is that this RPRCT data that we collect is differentially private, and individual level data can be shared to you guys. And you can replicate it just to make sure that we done our math correctly, we done our p-values correctly, and if you wanted to combine the data set. So this is a summary. We create a new design that preserves data privacy and while allowing estimated causal effects. This is also robust. A key part, I think, the more innovative, really cool part for us, at least to me, was this robust against cheaters by using this very simple sample splitting strategy of a slightly phased out, phased in spinner. It can estimate the AT among non-cheaters, and there's covariate adjusted ones. And we ran this trial in real life. We collected our own data. We found a significant effect, which is very, very happy for me and very happy for my student who got to graduate. And there's a characteristic about the efficiency privacy trade-off at the end of the day. There's some future directions. As Carlos mentioned, you can definitely estimate the proportion of cheaters with covariates. We didn't do it here because we had enough moments to estimate this parameter, but definitely you can get better estimates here. The problem is you have to then model this, and there's model misspecification that you have to think about. Optimality, here's another one. Is this the best possible analysis with the data that we're given? We don't know. I think it is, but this is for another student for another day. This is another thing is optimal design. Given that I have an epsilon privacy trade-off and I want to still identify the AT among honest cheaters, is this the best possible design that we have come up with? Or are there better designs out there in the universe that can do this? And then this one, I actually wanted to present this because we're currently working on this. You know, you probably talk class or you have group projects, and sometimes instructors assign the groups randomly, or you get to form your own groups. But the question for me was, and this is done a lot in peer experiments, it's very difficult to estimate causal effects about the differences between self-formation of peers versus not. And so we're currently actually in the midst of getting through the IRB approval for this. And there's different kind of questions that hopefully I can introduce to maybe a year or two from now. On all this. Okay. Well, thank you very much for your time. I appreciate it.
Thank you. So we are out of time, but if someone has a question, we could take a few minutes for a question. Also, people on Zoom, if you can hear, you feel free to raise your hand. We did get a lot of questions during the talk, so maybe we've exhausted all the questions. All right. Well, if there's no questions now, let's thank
Thank you. Also, just before we conclude, I just wanted to thank, I forgot to do this. I want to thank all my PhD students, not just my own, but also every PhD student who helped me with this. It's during COVID. I know it's really hard, but I was able to convince people who took my causal inference course to actually help me run this trial, as well as the administrators who was really generous and kind enough, went out of their way to run this, as well as several instructors at the end. So I just wanted to thank them for all their effort. Yeah, thank you. Yeah, thank you again for being listening.
All right, thank you all. See you next week.